Welcome back, everybody. This will be our last video of the week. That's week 7, and that's our lab 7 guided activity. So we just ran a bidirectional test to answer the question of whether the sleep patterns of cats are different from the sleep habits of dogs, when we know that dogs sleep 16 hours. Now imagine that we're going to make this directional now to make sure you're ready to figure out how to grab the correct piece of code and how to adapt it in each one of the cases. So a statistics student interested in sleep habits of domestic cats took a random sample of cats and monitored their sleep. According to online resources, domestic dogs sleep on average 16 hours a day. There are reasons to believe that in the wild, cats sleep more than dogs. The question of the student was whether domestic cats sleep more than domestic dogs. I want you to use statistical tools that you learned today to answer this question and consider an alpha level to decide of 0.05. The hypothesis. The null hypothesis is the same, that the average sleep of the population of cats is 16. And the alternative is that it is more than 60. So the data, again, meets the conditions to construct the sampling distribution of the mean using the central limit theorem. We looked at histograms and mean, median difference above, so that's all good. To know that it's not skewed, we have a large data set, and we can sort of assume independence because the observations have been randomly sampled, and we have a sample size that is not more than 10% of the population of interest, which is the population of domestic cats. Now, without actually running the test, do you expect the decision or conclusion to change? Yes or no? If you're thinking no, you are right, because if the p-value was significant under a two-tail test, it will continue to be significant on a one-tail test because it's going to be half that value, even smaller than that value, right? So no change will be expected. What can happen sometimes is that, say, if you run a two-tail test and you get a probability of 0.09 because you're summing the two tails. When you run a one-tail test, that will be half of that. That would be a 0.045, which then would be less than 0.05, and the decision could change. But when you have a very extreme p-value, things tend to be the same regardless. But again, you should not pick a one-tail test just to make your statistics significant. You should pick a one-tail test when you have a directional hypothesis. And it's not likely that things will ever go the other way. So I would not expect that to change this time. In question 8, I'm asking you to run a one-tail z-test to interpret the results. Let's look at our hypothesis. Our hypothesis is related to the average sleep being greater than. So we need a unidirectional z-test that looks like that. So let's find it. So that's a two-tail. That's not what I need. Let's find there. So these are the codes you need if you were to run z-tests with a directional alternative hypothesis, right? So we want one that has the mean expected to be greater than some value. So this is the one we want. Let's go there and put the test there. Oh, sorry. Let's change things around. So here we need cat data. I forgot to adjust. Here we need cat sleep. Here we need cat sleep again. Everything else is the same. Oh, the null hypothesis is not 100. It's 16. All right, so the p-value is very, very, very tiny, even tinier than before. So the conclusion is that data indicates that the probability of observing in a sample of 143 domestic cats a mean number of hours of sleep greater than 1799, if the null hypothesis were true, is very, very small, right? Less than 0.0000. It's 119 zeros, right? This probability is smaller than our critical value of alpha, set to be 0.05. Therefore, the decision is to reject the null in favor of the alternative hypothesis. The confidence interval is a good metric to quickly support the decision. As noted before, we need, however, to pick the appropriate coefficient confidence interval given the alpha level and type of test, directional versus non-directional. In the case of a non-directional test, we want to pair it with a confidence interval of 95%. In case of a directional test, we want a confidence interval that puts, where's my 90%? Let me find it. Where is it? Let me find it and come back to it. So now I found it. Hang on. So here is it. So with the 90% confidence interval, remember we have 90% of the data in the middle, and the rejection area, I'll be just looking at one side, either smaller or larger, but we'll put the full 5% on one of the tails for the rejection area. So we make the rejection area larger on one side, right? That's the one we're looking at, because we consider it impossible that things will go the other direction for one reason or another, theoretical or practical. Okay, maybe you have prior evidence that either cats sleep more or no, it won't be different, right? You know that less is not the case. So you have a full 0.05 rejection area to consider. So that's why we map one tail test with a confidence interval of 90% so that the results kind of pair up together. So let's go back to our RMD. And here I'm asking you to compute the 90% confidence interval of mean sleep time. So we need to grab the code for confidence interval, which is here. And because here it's already the confidence interval for the cat data, you don't need to adjust much, except that there we computed the 95% confidence interval to go together with the two-tail test. Here we want the 90% confidence interval instead. And for that, we need a different Z critical, right? Like I was showing to you from class, when I have a 90%, we want a Q norm of 0.05 because that's the full area I'm leaving for rejection on one side, has the full 5% probability. And so I have to change this piece. And the rest will be the same. It will be a slightly tighter interval between 17.884 and 18.12. So final conclusion, the first part of this conclusion exactly the same, right? Exactly the same thing before, except change the numbers a bit. P-value is different, and 90% confidence interval is 17. So again, literally, the conclusion is exactly the same, right? From what we had before. Let's see here. This is, instead of saying, let's say it's identical, let's copy and paste there. So you have it in the key. Data provides sufficient evidence that the sleep patterns of cat is different. So the Z value is exactly the same. The P value is half the other one, but because the other one was already knocking out of the park, 0.000, 112 zeros, and the other one was 119 zeros. It's all less than 0.00001. And before we said we were 95% confidence. Here we say that we're 90% confident that the average hours cats sleep is between this one, 17, let's say 1784, 85, let's round it, and 1813. So that's it. In your homework, you have to test a hypothesis as well, and I will have you do that with a different data set that we'll then discuss at the beginning of the following class. All right? Have fun trying to do it. If you have questions, please come to our live meeting on Wednesday. All right? See you there. Bye-bye.